So today let's make a third episode of my Spark Gap Tesla Coil series, and this episode is going to be about this capacitor. And you probably say the entire episode about just a capacitor, such a simple component. But trust me, a capacitor for a Spark Gap Tesla Coil is quite a tricky component. It's not easy to buy or make this capacitor. It's maybe even the most tricky component of the entire Tesla coil, a Spark Gap 1. Despite it looks like one small component in the schematic. I think that it may be the hardest to make or the most expensive component of a Spark Gap Tesla coil, because you can get the high voltage transformer from scrap if you're lucky. The Spark Gap is just two or a couple pieces of metal electrodes and maybe a fan cooling it. The primary is just a couple turns of a thick wire, it's just like 3, 4, 5, 6 turns. And the secondary is a bit trickier because it contains like 1000 to 1200 turns. But it's still kind of cheap to make, and you can also use some used wire from some coil, from some winding, which is not in resin, so you can unwind it and get a wire for free, and the pipe for it can be some pipe for drains, which can come from scrap or you can buy it. This one is about 50 centimeters and 10 centimeters or 11 centimeters diameter, and it's for about $2 or $3. And a 1 meter long one can be about $4 or $5. So the secondary can be tricky to make, but the capacitor can be actually even worse. It's either going to be the hardest component to make or the most expensive one to make, or the component that fails most often. The first capacitor that people usually try to make is some kind of Leyden jar with aluminum foil around it and some salty water inside of it as the other electrode, or some aluminum foil from both sides of it, or maybe some plastic container instead of glass, or maybe stacking some glass panels, some glass rectangles and aluminum foil in between, or maybe using some plastic foil and rolling it together with aluminum foil, or some kind of material, plastic material for floors, some PVC or something like this. When I was a poor student, I tried this, basically just a roll of trash bags, one layer of aluminum foil overhanging it on one side, then another layer of trash bag roll and another foil overhanging it on the other side, like this. And then I basically rolled it, and it was a capacitor, and it worked for some time, but it soon failed. It actually worked in a small Tesla coil, but it wasn't very efficient, it was quite lossy, it was getting hot, and it failed very soon. This plastic layer basically just broke down. And of course I also tried various glass panels. Now imagine this is glass. I was alternating glass panels with aluminum foil, overhanging on one side, another glass, overhanging on this side, another glass. The next one is again on this side, another glass, this one is on this side, and so on. And you get basically electrodes on each side of it. And this kind of glass capacitor actually worked for some time, but also not that efficiently, and finally one of the glass panels cracked and it arced over. And maybe some material like polypropylene would work better. It's the same material as this pipe and also the same material as some high frequency or pulse operation capacitors. Capacitors for pulsed or high frequency or high current applications are usually made of polypropylene because it has a very low dissipation factor. Maybe it's possible to make a capacitor out of polypropylene pipe for drains, but it would be quite huge. And finally I got the best results using a Multi Mini Capacitor. It's a big capacitor made of a lot of small capacitors, in series or in series parallel combination. In a Multi Mini Capacitor you basically put more capacitors in series for more voltage rating, but you can also put more in parallel for more capacitance and to spread the current across more capacitors. Because the pulsed current in a Spark Gap Tesla coil is quite high. So you basically put more capacitors in series for more voltage, but this also reduces the capacitance. You get 3 times the voltage if you put 3 capacitors in series, but also 3 times less capacitance. So for more capacitance, you have to put more capacitors also in parallel. And it's also a good idea to put a discharging resistor on it, or actually discharging resistor on each capacitor like this. And because you don't want to put a chain of resistors on each chain of capacitors, you can put the capacitors in parallel like this. So there is one resistor for entire parallel group, instead of one resistor for just one capacitor. Let's have another example. Let's build a capacitor bank out of those capacitors. If you put 4 in series, the capacitance divides by 4. So it's now just 25 nanofarads. But the voltage multiplies by the number of capacitors, so it's now 4 kilovolts. So if you put more capacitors in series, you get more voltage rating. It can basically take more voltage, but it also reduces the capacitance. You basically multiply the voltage rating by the number of capacitors, but you also divide the capacitance by the number of capacitors. If you put enough capacitors in series to be able to take the voltage, you usually end up with a too low capacitance, so it's necessary to put another capacitors in parallel. Like this, and as I said, it's better to connect it like this, so that you can put also resistors on it like this, and you have just one resistor for each parallel group, to make it simple, instead of using one resistor for each capacitor. And those resistors are not necessary, but they are very good for safety, because when you turn it off, those resistors discharge the capacitors. Without those resistors, the capacitors remain charged to a very high voltage. And a capacitor bank for a Tesla coil can be quite dangerous. The energy in it can be potentially deadly. So those resistors are really quite important for safety, and they also help to balance the voltage between the capacitors. And in this example, I put 4 capacitors in series and 2 in parallel. So the capacitance divides by 4 and multiplies by 2. So it ends up as 50 nanofarads. It's a simple calculation. And the voltage rating depends on just the number of capacitors in series. It doesn't depend on the number of capacitors in parallel. So it stays 4 kilovolts. But this is going to get even more tricky, because a Spark Gap Tesla coil puts quite a lot of stress on the capacitor. Not only the capacitor has to have enough capacitance and it has to handle a very high voltage, but it also has to handle a very fast changing voltage. The capacitor basically has to be able to charge or discharge super quickly at a super high current. The capacitor has to be able to take very quick changes of voltage, a very fast rate of voltage rise or voltage slew rate. In a datasheet of the capacitor, it's usually called dVdt, and the unit is volts per microsecond. It basically tells you by how many volts the voltage on the capacitor can change in 1 microsecond. So when choosing capacitors for a Tesla coil, this rating of the capacitors have to be as high as possible. It should be at least in hundreds of volts per microsecond, or even better in kilovolts per microsecond. You basically have to use some special capacitors for high frequency operation or pulsed operation. You definitely can't use any random capacitor. So you're not just looking at the voltage and capacitance, but also at this rating, which should be as high as possible, and those capacitors are usually called pulse operation capacitors or high frequency capacitors, and they are usually polypropylene. It's the material of the isolation between the electrodes, basically. And they should be metal foil, not just a metallized film, which is just a super thin conductive layer on a plastic film. But of course the capacitance and the voltage rating is also important. If you have a too low capacitance, you have to put too many capacitors in parallel. And the voltage rating is even more important, because if you have a too low voltage rating, you have to put a lot of capacitors in series. But if you put more in series, it reduces the capacitance, so then you also have to put more in parallel. So a lower voltage rating means more capacitors in series, but also more capacitors in parallel. In the worst case, you can use probably 630 volt capacitors, but in this case you're looking for higher capacitances, like this. It has to have enough capacitance, but still not too high, because it's better to put more capacitors in parallel to spread the current. The peak current in a Spark Gap Tesla coil can be like hundreds of amps. Now the question is what has to be the voltage rating of your capacitor bank and how many capacitors you have to put in series. It depends on the voltage of your high voltage transformer, of course. It has to be rated at least for the peak voltage of your high voltage transformer. And the peak voltage of a sine wave AC voltage is the AC voltage times the square root of 2, which is about 1.414. Plus, of course, some headroom. And how much headroom? That's not an easy question. It depends on how reliable you want it to be. But of course it's better to spend a little bit more money on a capacitor that can last forever than wasting a little bit less money on a capacitor that's going to blow up in seconds. And of course how much headroom you need also depends on how long you want it to last. If you basically want to take just a couple pictures and make a short video and disassemble it, you don't need that much headroom. But if you want to show it to some audience often, you really need more headroom. If it has to be reliable in the long run, it has to be really seriously designed. But most people who build Tesla coils say that the voltage rating should be about double of the peak voltage of the high voltage transformer. Some conservative people even say 3 times the peak voltage. Now let's do some calculations. This is the voltage of my power supply or transformer with 4 microwave oven transformers in series. Now the peak voltage of this AC voltage is this times 1.414 and this is about 12 kilovolts. If I double it for headroom, it comes out as about 24 kilovolts. So for some reasonable reliability, the capacitor should be rated 24 kilovolts for my power supply. And some people would even multiply it by 3, which will give about 36 or 37 kilovolts. So the voltage rating of my capacitor is going to be something like 24 to about 36 kilovolts. My previous Spark Gap Tesla coil had a power supply with 3 mods in series and the voltage was this, so the peak voltage of it was this. And the capacitor bank was 90 pieces of those capacitors, 100 nano, 1500 volts, 6 in parallel and 15 in series. So it resulted in 40 nanofarads and 22.5 kilovolts. And so the headroom was 2.43 times the peak voltage of the power supply. And the new power supply is basically 4 microwave oven transformers in series and the mains voltage added to it, so it has this output voltage and the peak voltage of it is this. This is roughly the reasonable range of capacitor bank voltage rating. And now let's take a look at my capacitors, which I was able to get in a reasonable quantity. I have 400 pieces of them. Let's take a look at them. Those are 180 nano, 1 kilovolt. And they are from 1989, as you can see, but still quite nice polypropylene pulse operation capacitors. Made by Tesla, 180 nano, 1000 volts. And several of those boxes are going to be my capacitor bank. And they are rated 1000 volts, so I need about 24 to 30 in series. So here's my cat on my calculations and let's take a look at it. So I decided to put 28 capacitors in series, and of course the voltage adds up, so it gives me 28,000 volts DC rating. And also here you can see some other data of the capacitors, those ones, and they are 1000 volts DC, 350 volts AC, and their maximum DVDT is 750 volts per microsecond. So 28 capacitors in series have this voltage rating for DC, this AC voltage rating, and also this DVDT rating also adds up when you put capacitors in series. So in total this is going to have 21,000 volts per microsecond. And 28,000 volts divided by 12 kilovolts or 12,200 volts is... My capacitor bank is rated for 2.3 times the peak voltage of my high voltage transformer. So there is more than double headroom. And the AC voltage rating of my capacitor bank is also higher than the actual AC voltage of my transformer. So I decided for 28 capacitors in series, but I still don't know how many in parallel. So let's calculate the capacitance of the string with 28 series capacitors, but not yet putting them in parallel. So the capacitance 180 nano is going to divide by 28, and it gives me 6.42 nano. So this is the capacitance without putting them in parallel, and I aim for about 50 nano. So 50 nano divided by this, 6.43, is about 7.7 capacitors in parallel. But of course it has to be a whole number, so let's round it up to 8 capacitors. And now 180 nano divided by 28 in series and times 8 in parallel gives me about 51 nano. So let's decide for 8 capacitors in parallel. So in total I need 224 capacitors. So I've calculated my capacitor bank, and the DC voltage rating is fine, the AC voltage rating is fine, and now, is this dV/dt rating fine? So let's take a look at this calculation of the peak dV/dt of a sine wave AC voltage. So the peak dV/dt is basically the voltage, the AC voltage, times the frequency times tu times pi times the square root of tu. And the maximum high frequency AC voltage is probably going to be the same at most as the low frequency AC voltage from the transformer, because this is the voltage from the transformer and the spark gap triggers probably at most at its peak. You can't get more voltage than this, and now it starts oscillating at a high frequency. So the initial amplitude of this high frequency oscillation is the same as the amplitude of your low frequency AC voltage from your transformer. And so this is the highest theoretical voltage, because in reality you have to set your spark gap to trigger a little bit under the peak voltage so it can reliably trigger. Because if you set the spark gap to trigger above the peak level, it doesn't start up. If you have a static spark gap, it always limits the voltage below the peak level of your input AC voltage. If you have a rotary spark gap, and my kit on my schematic, hey, you are sitting on my high voltage. If you have a rotary spark gap, then the voltage can actually peak higher, because now the spark gap triggers, the oscillations go out, and now the transformer was basically shorted out by the spark gap, and when the spark gap quenches, the short circuit is basically removed from the transformer, and the voltage can actually overshoot higher. Because in a rotary spark gap, the electrodes can go quite far away from each other between the cycles. And this is also the reason why a rotary spark gap Tesla coil also has to have a safety spark gap to limit those overshoots, because otherwise it can damage your transformer or the capacitor. But if you have a static spark gap, the safety spark gap is probably not that necessary, because the main spark gap always limits the voltage. It's always there. And I plan to use a static spark gap, so let's consider that the ignition of the spark gap happens at most at the peak of the sine wave from the transformer, so the maximum peak voltage of those high frequency oscillations is the same as the peak voltage of my transformer. So the initial high frequency voltage here is going to be the same as my transformer voltage, which is 8630 volts. So let's put it into the calculation. Here is the voltage, and the next one is the frequency. The primary frequency has to be the same as the secondary frequency, and my design of secondary is probably going to be 220 kHz, which is 220,000 Hz, times tu times pi times the square root of tu is... And of course this comes out as a crazy number because it's in volts per second, not volts per microsecond. So let's divide it by 1 million. And it comes out as 16,870 volts per microsecond. So here's the result with my kit on it, and she probably doesn't want to admit that it's too complex for her, and this value is actually lower than the maximum rating of my capacitor bank. So it should be fine. My capacitor bank is rated 21 kilovolts per microsecond, and the actual peak dV/dt is going to be just about 17 kilovolts per microsecond. It's not that much headroom, but this is the worst case maximum peak. The spark gap basically triggers here and you get a high frequency sine wave, which slowly fades out, like this. And this peak DVDT only happens here, when you have the maximum amplitude, but also you are in the steepest point of a sine wave. So this is heaps of theory, but now it's time to actually build my capacitor bank. 28S8P. 224 capacitors, and those boxes are 50 each, so I need 4.5 boxes basically. And I decided to split it in 2 series halves for easier transportation, but also to reuse those capacitors in a smaller Tesla coil with just 2 microwave oven transformers. For half the voltage I can use just one of them or those 2 in parallel. Or maybe I can also try a symmetrical system like this with 2 capacitors. This could theoretically halve the high frequency voltage in reference to ground, to reduce the interference and also corona discharges. I decided to measure them and also sort them to kind of match them. I sorted them by capacitance, and this looks like a distribution chart of the capacitance basically. The ones with a more similar capacitance will go into one series chain. Similar capacitances should go in a series so the voltage divides more evenly. The sorting goes on. In some of the boxes the capacitors have different color of the plastic housing. That's weird. They are made in a different month but the same year. So I've sorted 6 boxes, 300 pieces. As you can see, most of them came out as plus minus 10 nano at most, and there are just 4 pieces significantly below the nominal. So let's basically sticky tape it together in groups, so it stays together before I solder it and before I put the copper wires for connections on it. So it's sticky taped together. Now I put some spacers between the rows to have some air ventilation, some air circulation for cooling, and then of course I sticky tape it all together. And now it's sticky taped together, and this is 1/4 of the total capacitance, with some ventilation holes. So this is 1/2 of the capacitor bank mechanically together, but it still has to be soldered, of course, and the resistors have to be added. I could probably have it like this, but for less stray inductance and to share the current better between the capacitors, it's better to make it more compact, like this. Some spacers, and let's put it one on another, like this. And sticky tape it together. And this is a horrible sticky tape construction, but as long as it works, it should be fine. And now of course soldering time. I have to solder it all together and put some terminals on it, like this. Soldering it and putting the resistors on it. The soldering goes on. And finally, here's the finished capacitor, or actually 1/2 of it, with all the capacitors connected like this, all the resistors on it, 14 resistors, and the capacitors from the other side, and some connections, and the terminals. The terminal on one side, and on the other side as well. And of course my cat, which likes it. And now of course measuring time. The capacitance of it should be 180 nano divided by 14 in series times 8 in parallel is 102.8 nano. And it actually is 102.7 or 8. That's exactly it. And the resistance of the resistors is, of course it takes some time to charge the capacitors, and it approaches 14 mega ohms because there is 14 resistors in series and 1 mega ohm each. Those are 1 mega ohm 2 watt resistors. And of course, one thing I forgot to mention earlier is that the capacitor shouldn't resonate with the transformer. The capacitor has some resonance frequency together with the inductance of the transformer, but this shouldn't be the mains frequency. Because of course the transformer has some inductance, either internal inductance because of the magnetic shunt in it or external inductance, some inductor to limit the current. And it doesn't matter if the inductor is on the primary side or secondary side. The inductance still transfers from the primary side into the secondary side and it can resonate. The resonance could basically boost the voltage to a point where it destroys the transformer or the capacitor. So it should be avoided, but of course there is this spark gap which would probably clamp the oscillations. So in reality the voltage wouldn't probably go much above the normal level anyway. Especially with a static spark gap. With a rotary spark gap it can be a bigger problem, but if you use a rotary spark gap you should use a safety spark gap. The safety spark gap is usually in parallel to the normal spark gap. But if it's a center-tapped transformer, which has the center grounded, like this, the spark gap basically is double. The safety spark gap is basically 2 spark gaps, each of them protecting 1/2 of the transformer secondary. This is especially important if you have a rotary spark gap. It may not be necessary if you have a static spark gap. The static spark gap basically clamps the voltage all the time. And when it's ignited, it basically also shorts out the high frequency current, so it can't go back into this transformer. The only problem then is the common mode high frequency current that goes back. And the common mode high frequency current is still clamped by this safety spark gap. But the common mode high frequency current can be also reduced by using a split capacitor. This kind of symmetrical system basically with 2 capacitors. I'm going to try this system, it seems to have many advantages. So here's the specification of 1/2 of it and the specification of 2 in series. And according to my calculations, this resistance should discharge the capacitor from the full voltage 28,000 volts to a safe voltage 30 volts in 9.8 seconds. So in 9.8 seconds, after turning it off, it should be safe. But if the resistors fail, you should probably still try to discharge it using some special high voltage insulated tools before touching it. The energy in the capacitor at its full voltage is about 20 joules, which is already a potentially deadly energy. It's better not to rely just on the resistors, they could fail. So this is Wild, and see you in my next videos, and thanks to all of my patrons on Patreon, I really appreciate your support. And the next episode is probably going to be the secondary, on a polypropylene pipe and some wire of course, to wind it.